Hi everyone. In this video, we will demonstrate that not all subsets of the reals are measurable. In particular, we will do this by constructing a non-measurable set. As we progress through this video, we will be just looking at the construction of one example of a non-measurable set. I encourage you to pause the video as we go through. We will establish a number of claims about this set once we have described it. I encourage you to pause the video along the way to make sure you understand each claim. And then the second to last slide of the video, we will actually prove that the set we have constructed is non-measurable by using the claims we have established along the way. So to begin, let's describe this set. So imagine you take the interval 0, 1, closed at 0 and open at 1. And on this set, we want to define an equivalence relation. So we will say x is equivalent to y if and only if the difference between x and y is a rational number. So just to begin with, we'll take this step by step. So just to make sense of this, we're defining an equivalence relation where two things are equivalent if and only if their difference is a rational number. So for example, 0 and 1/2, they are both in x, right? And 0 is equivalent to 1/2 under this equivalence relation because the difference between 1/2 and 0 is just 1/2, which is a rational number. Okay. Similarly, okay, we could take, let's see, what should we take? Let's take pi over 4. And let's take, so that's certainly between 0 and 1, and let's take pi over 6. If I look at their difference, pi over 4 minus pi over 6, I'm going to do that in absolute values, but in this order, the difference will be positive. So if I look at this difference, this is pi times 1/4 minus 1/6. 1/4 would be, we need to do twelfths as the common denominator. So this would be 3/12 minus 2/12. So the difference here would be pi over 12. Now, pi over 12 is not a rational number, and therefore pi over 4 is not equivalent to pi over 6. Okay. However, one final example here, if we were to take, say, pi over 4 and pi plus 1 over 4, I should be a bit careful here. Let's take pi over 6. Pi plus 1 over 4 is not in x. So I need to be a little careful here. Let's do pi over 6 plus pi plus 1 over 6. Their difference will just be 1/6. So these two are equivalent to one another under this equivalence relation. So we're just defining this equivalence relation. Okay. One of the things to notice from these examples is, in fact, all rational numbers are equivalent to one another, but not all irrational numbers are equivalent to one another under this equivalence relation. So these two are equivalent to each other, pi over 6 and pi plus 1 over 6. Those are both irrational numbers, and they are equivalent to one another. But these two irrational numbers are not, right? So you have all this equivalence relation. You can think of all the rational numbers are equivalent to each other, and then it sort of breaks it up into different classes of irrational numbers that are equivalent to each other. Okay. And so indeed what we can do is, excuse me, we can think about the fact that this equivalence relation partitions my set X. So what I can imagine doing is I take my set X and I start partitioning things up into different sets depending on whether or not they are equivalent to one another. So for example, right, you can imagine I have one equivalence class, which is going to be all the rational numbers. So 0's in there, all the rational numbers, 0, 1/2, 3/4. Again, there are lots of other things in here, right? This one equivalence class is all the rational numbers, okay? But then, like we saw, there's another equivalence class, say, that has pi over 6. It has pi plus 1 over 6. In fact, it has, I mean, if you put anything, pi plus 2 over 6 would be in the same equivalence class. But there are a lot of other things that we can't really name, okay? But then we showed that, for example, pi over 4 was not in that same equivalence class. But for example, pi minus 1 over 4 would be in this equivalence class. So it's a set of all of these things are equivalent to each other under the equivalence relation. All of these things are equivalent to each other under the equivalence relation, so on and so on. So you can partition your set X into all of these equivalence classes, and everything in X will fall into one of these equivalence classes. Okay. And so the idea is I'm going to construct a set capital H by going through each one of these equivalence classes and just picking some representative. Okay, so maybe 0 might be the representative from this equivalence class, and pi over 6 might be the representative from this equivalence class, and pi minus 1 over 4 might be the representative from this equivalence class, and so on and so on and so on. Okay. Now, I do actually have to invoke the axiom of choice here. So I have a bunch of non-empty sets. I have an infinite number of non-empty sets, and I want to go in and pick one element from each. So that requires, if you've read any about the axiom of choice or about mathematical logic, this requires this assumes the existence of a choice function, right? And so I am using the axiom of choice here. In analysis, we fairly freely use the axiom of choice. So I'm going to go through and pick one of these out, one representative from each equivalence class, and that is how I'm going to form my set H. Okay. So now, what I want to do over the next few slides is I want to prove some claims about this set H. Okay. Now, one of the things that I'm going to be doing, and this is something we've done before, but I'll just remind you, is I'll be looking at times at, say, the set H plus some number R. So just recall, this is the set of all elements of the form R plus little h, where little h is in capital H. So this is just the definition of a set plus a number here, okay? And so I'm going to just prove a number of properties. And then once we understand some properties of this set H, then we will use those properties to prove that, in fact, this set H cannot be Lebesgue measurable. All right. While I'm erasing here, I'll mention this construction is really due to an Italian mathematician named Vitali. And these so-called Vitali sets are really the sort of prime example of a non-measurable set. So if you're interested in seeing, there are other ways of constructing Vitali sets. And in fact, you can actually define many sets which are Vitali sets. So we're looking at a particular Vitali set. But these Vitali sets are the typical example of a set that is not measurable. All right, so let's look at some properties of this set. So the first thing I want to claim is that this interval 0, 1, okay, so this is just what I called X earlier, right? I want to show that this is a subset of the union over all rational numbers between -1 and 1 of R plus H. So what you can think of these R plus H things, right? They are these R plus H's. These are all different sets, right? I'm unioning them over all these different rational values. Okay, so let's see if we can prove this claim. So fundamentally, yes, maybe this looks complicated, but I'm just showing that something is a subset of something else, right? So how do I do that? Well, let me take an arbitrary element of this set X of 0, 1. Okay. Well, y, since it's in this is my set X, right? It lies in some equivalence class that was formed when I partitioned X by that equivalence relationship. So I can say then y lies in one equivalence class. And in fact, it lies in exactly one equivalence class. In the partition of X by our equivalence relation. Well, so Y was in one of those equivalence classes. There's some H, right? We picked some H out to be the representative from that equivalence class. Okay, so let's call little h be the representative um, oops, getting some caps off here. Now this be the representative of that class. So that, okay, so that means H was the chosen representative, so it ended up in my set big H. And since H was in the same equivalence class as Y, that means that the absolute value of Y minus H must have been a rational number. Right? I don't know what it was, but it had to be in Q, right? And in fact, this R, if you think about H is a representative, so it was in X, Y was in X, right? And so these also could not have been, right? The worst off, essentially, this could have been, would have been, the worst this distance could be would be 0, 1. Okay. So what does that mean? Well, then, looking at this equality here, that means y minus h is equal to, and sorry, here, instead of calling this r, because I'm going to need something else in a minute, let's call this little q. So then this means minus y, or y minus h is equal to either plus or minus q. And so that means y is equal to h plus or minus q. And I don't know which one, but y is either equal to h plus q or h minus q, right? It really depends on whether y or h was larger. Okay. Well, that means that y must be equal to h plus, now this is where I want to use r, h plus r for some, well, let's see, q was a rational number between 0 and 1. Plus or minus q then, well, it was either between -1 or 1. Okay, so hence, y is equal to h plus r for some r, which has to be rational, but could be between -1 and 1, because basically r is plus or minus q, right? And q had to be strictly between 0 and 1. Okay. Well, what does that mean? That means then that y is equal to something in the set H plus a rational number for some rational number here. So y is in R plus capital H for some rational number r between -1 and 1. And since it's in one of these, then it must be in the union of all of them. And hence why I must be in the union over all rational numbers between -1 and 1 of r plus h. All right. So everything between 0 and 1, including 0 but not including 1, is contained in this union of these sets. And we sometimes call these, we might call these like cosets. These are really, one way to think of these, if you've seen some algebra, these are like sort of like cosets of the rationals, right? So you have this equivalence relationship, and you form this these cosets. All right. Now, let's think about this again. We're just proving things about h right now. Eventually, we're going to use all of these things to show that h can't be measurable. But if I sort of think about this, what is this? Like, what sort of things do I see that might be useful in proving something about measure, right? Well, I see on the left-hand side an interval. That's a really easy thing that's a really easy thing to take the measure of, right? I also have a claim about a subset, so I can use things like monotonicity, potentially, or countable subadditivity. I also see here a countable union, right? There are countably many things here, right? Start to think about, again, countable subadditivity or countable additivity, either one, right? So in order to use countable additivity, though, right, I would need something else, right? Namely, I would need that each of these things is disjoint, okay? But again, I see some things that feel like things I could use to prove something about measure. All right, let's prove the other. Let's prove a subset containment, but now in the other way. So now I want to show that this union, this is the same union from the previous claim. This union over all rationals between -1 and 1 of r plus h is a subset of the interval -1 to 2. Okay. This is actually a fairly quicker proof. Okay. So take some element, let's call it z, in this union. Well, then it lies in one of these, right? Since it lies in the union, it lies in at least one of these. And so I can write z as some rational number, r, plus some h, right, in h, right? So it's in one of these. So z has to be in some r plus capital H. And since it's in there, it means there's some little h in capital H such that z can be written as r plus little h. So this holds for some r in q intersect -1, 1, and some h in h, which, remember, all of the things in h are coming out of that set x, right, which are all between 0 and 1. Okay. Well, if I look at r, all my r things are between -1 and 1. And all my h things all of my h things are between 0 and 1. And I'm going to be, again, it sort of doesn't matter here. I can be a little lazy about this. Okay, it's strictly less than 1, but I'll put less than or equal to 1. Well, then what can I say? Well, then z, which is r plus h, Well, the biggest it could possibly be is 1 plus 1, which is 2. The smallest it could be is negative 1 plus 0, which is negative 1. Okay. So z has to be between negative 1 and 2. So z is in negative 1, 2. All right. So now I actually have this union is trapped between these two intervals, right? On the one hand, it contains the interval 0, 1, including 0 but not 1. It's contained within the interval minus 1 to 2. Now, again, notice I'm not sure about the measurability of this thing yet, but if it is measurable, then certainly by monotonicity, right, its measure must be somewhere between 1 and 3. Okay. So I don't know what the measure of that thing might be, but it's got to be between 1 and 3 by monotonicity, if it is indeed measurable. All right. Now to our final claim before the proof. Okay. I want to show that if I take one of these sets R plus H and I intersect it with another set Q plus H, where R and Q are both rationals between minus 1 and 1, and R and Q are different rational numbers. If I do that, I get the empty set. Now, before we prove this claim, let me actually show you why we care about this. Remember, we've been looking at this union. R is in Q intersect minus 1, 1 of R plus H. Really, what we are proving here is that for any two different values of R, these sets are disjoint. So what we're doing is we're actually showing that this is not only is it a countable union, it's a countable union of pairwise disjoint sets. That sounds like something that would be helpful in applying something like countable additivity, right? So really what we're doing here is we really are proving something again here about this union. We're showing that everything, each set in that union is pairwise disjoint. All right. So how do we do that? Well, this seems like a good place for a good proof by contradiction. Okay. So let's suppose to the contrary that this isn't the empty set. Okay. So suppose to the contrary you have some element, we'll call it Z, which is in R plus capital H, and it's in Q plus capital H. Again, with R not equal to Q. Okay. Well, since Z is in R plus H, that means that Z is equal to R plus H1 for some H1 in H, and Z is equal to Q plus H2 and again, these hold for some H1 and H2 in H. Okay, so we're just following, we're supposing to the contrary that there is something in the intersection. We're just writing out right now the consequences of that. Now note that I'm going to write 0 as Z minus Z. Okay, and I'm going to use both of my expressions for Z here. So this will be R minus Q plus H1 minus H2. So I just take R plus H1 minus Q plus H2, and I rearrange it in this way. Okay. Now, what does that tell me? So another way I could write this is if I rearrange this to the other side, or sorry, if I move this to the other side, that means that H2 minus H1 is equal to R minus Q. R and Q are both rational numbers. Well, wait, if H1 and H2, if their difference is a rational number, then one of two things is true. Either H1 and H2 are actually the same thing to begin with, or H1 and H2 are in the same equivalence class, which would mean they can't both be in H, because we only chose one element of each equivalence class to be in H. Okay, so we can say then it must be that H1 equals H2. Since otherwise, H1 and H2 would be distinct elements of the same equivalence class. Of X. All right, well, great. So then I've got Z must be equal to R plus H1 and Q plus H1, right? Because H2 has to be equal to H1. But wait, this implies that R must be equal to Q, right? So if you solve here, R has to be equal to Z minus H1, Q has to be equal to Z minus H1. So R has to be equal to Q, but this is a contradiction since my assumption was that R and Q are not equal to each other. Okay. So it must be the case that you can't have the same thing in both of these sets. All right. Now, again, what we're really showing here is that all of those things we've been looking at in the union, all of those sets that comprise that union are pairwise disjoint. That's what we've really proven. All right, now it's time to put all of these results we've been proving to work. Okay. Now it's time to show that this set H, in fact, is not Lebesgue measurable. Now, you could imagine that somehow we're going to go, if you think about sort of the definition, right, that Carathéodory condition, you could imagine that we're going to go back and somehow show that that fails. But that's actually not what we're going to do. We're going to show that if we use just some of the properties of Lebesgue measure, we reach a contradiction. So let's look at that. All right, so here's my claim. Oh, sorry. All right, so my final claim, this is now the proof that this set H is not measurable. Okay, so suppose to the contrary it is. All right. Well, if H is measurable, then right here. then R plus H is measurable. Well, really for any real value of R, but certainly for any rational value of R between -1 and 1. Okay. This is translation invariance, right? So since H is measurable, R plus H is measurable by translation invariance. Okay. Well, then if each of these R plus H's is measurable, then certainly the countable union of all these is measurable. And this is due to the fact that the set of measurable sets forms a sigma algebra, right? And so the countable union of measurable sets is measurable. All right. And now we want to apply, we know this is measurable. Now we want to apply countable additivity here. Okay. So since the R plus H, so let me just sort of think of the collection of all of these are measurable. Again, I'm going to start abbreviating this. They're measurable. And not only are they measurable, they're pairwise disjoint. By countable additivity, we get that the measure of this union is equal to the sum overall rational R between -1 and 1 of the measure of R plus H. But if I look at this by translation invariance of the measure, okay, this is just equal to a sum, countable sum, of the measure of H. So really, you're just adding together the measure of H a countably infinite number of times. So you're adding it once for every rational number between -1 and 1. Okay. Well, that really only leaves us two possibilities. If the measure of H is 0, then this sum is 0. If the measure of H is non-zero, then this sum is infinite. Okay. So this is equal to either 0 if the measure of H is 0, or infinite if the measure of H is positive. Okay? I'm assuming that it's measurable, but I haven't assumed what its measure is. So if it's measure 0, then I get that the measure of this union is 0. If it's infinite, then I get, or sorry, if it's positive, then I get that the measure of this union is infinite. But this is a contradiction. The measure of this union, I proved that this union contains 0, 1, and this union is contained in -1, 2. So since 0, 1 is contained in this union, and I'm going to stop writing what this is the union overall R, rational R between -1 and 1. and this is a subset of minus 1, 2, then by monotonicity of the measure, the measure of this union would have to be between 1 and 3, which is the measure of each of these intervals. But you see here we have a contradiction, right? I have that the measure can only be 0 and infinity, but also it must be between 1 and 3. This is a contradiction. Hence, h is not measurable. All right. I really like concluding our discussion of just Lebesgue measurability of sets with this example because it really allows us to practice using all of these different properties of Lebesgue measure and Lebesgue outer measure that we've been working on over the past several videos. So the question is then, okay, well, great, we have a non-measurable set, so what? From sort of a pedagogical point of view, I think anytime you're talking about some property that something may have, in this case, a set can be measurable. You really only fully understand it when you also can see where it fails, right? So this is an example of a non-measurable set, and it helps deepen our understanding of what it means to be measurable. But in another way, if we think about the process of doing mathematics and researching mathematics, we always start, and indeed in this case, we started with a wish list for measure. You have hopes, right? You have things you hope you can prove. And we want to revisit then for one last time that wish list and think about what this example shows us about our wish list. All right. So with our discussion, at least for just talking about Lebesgue measure of a set, complete, we can go back to this wish list, right? Our goal was to find a function mu that assigned a size to subsets of R. And we said that ideally, a measure would satisfy the following 4 properties. We wanted for each interval I, the measure of I to be just its length. Check, we've done that. We've proven that the Lebesgue measure does that. We wanted to show that the measure would be translation invariant. Check, we've done that. We wanted countable additivity for Lebesgue measurable sets. We've done that. Now, the last thing we wanted, right? We wanted every subset of R to be measurable. And now what this example shows us is that the set of Lebesgue measurable sets is a proper subset of the power set of R. Said another way, there are non-measurable sets, right? So unfortunately, this last item of the wish list, it fails. Now, we have shown some other things, like we've shown the set of all measurable sets is a superset of the Borel sets. So there is a rich variety of different kinds of measurable sets. It's not just some small subclass of the set of the set of all subsets, but there are still non-measurable sets. And so as we continue, we will have to at times worry about whether sets are measurable or not. It's not something that we'll be able to take for granted. This concludes our discussion of the Lebesgue measure of a set. If you will recall, our motivation for studying the Lebesgue measure of a set was to help us define something that we will call the Lebesgue integral. So in the next video, we will begin our discussion of defining measurable functions and their Lebesgue integrals.